continuing on with our topic du jour, we have an example in path coordinates and coordinate transformation. And there you go. Here's my Newt Dog cartoon. We do this. Okay, so here's the problem, and this is problem 11-141 out of one of the Beer-Johnston editions. We have a race car A is traveling on a straight portion of the track while race car B is traveling on a circular portion of the track. At the instant shown, the speed of A is increasing at a rate of 10 meters per second squared, and the speed of B is decreasing at a rate of 6 meters per second squared. For the position shown, determine the velocity of B relative to A and the acceleration of B relative to A. Right? So we're combining a bunch of things here together that we've done so far. We could even go a little crazy and start putting in the fundamental kinematic relationships as well, right? So we have like relative motion, and he's going to be a path coordinates. So we're going to have to do coordinate transformation. All right. So anyway, this is 200 kilometers per hour. Whoops, I'm pointing at the thing. There you go. There's 200 kilometers per hour, and he is 240. And let's see who's increasing speed. A is increasing speed, right? So he's got an acceleration here that's equal to 10 meters per second squared, right? And we'll just leave it at that. That's the acceleration of A. This guy, he's actually decelerating right there. But if we're going to put in this correctly, by the way, we'll say this is the acceleration of B, but say the tangential, right? We need to recognize that the changing in speed, decreasing in speed, is going to be that direction right there. And it's going to be a rate of 6 meters per second squared. So that's the 6 meters per second squared. We could also say that it was negative 6 times the tangential, right? So we'll draw a coordinate system, because I did already. And I'll even try to make this right here neat right here. We'll say that he's got a coordinate system, and this is like a little cheat little thing to do. There we go. Like that right there, right? So there's EN, and here's ET. Now, if we want to find the relative velocity and the relative acceleration of these, the only way we could, we would essentially what we're saying is we want to find the velocity of B with respect to A. So we need the velocity of B minus the velocity of A. We also need to do this same thing right here. So this is like our mission, B relative to A. So the acceleration of B minus the acceleration of A. But the only way we could subtract out these vectors is if we have them in the same coordinate system. So maybe I'll go ahead and write out what these vectors that we know are. We were given in here. So we have the velocity vector of A is going to be equal to 240 I, right, plus 0 J. Kilometers per hour, everything is in kilometers per hour, so we don't necessarily need to convert anything. Velocity of B, and maybe I should change this right here. So the acceleration of A is equal to 10 I plus 0 J kilometers per hour. Now we come over to B, and because of his location right there, it's going to make it a lot easier for us to write it in tangential and normal components. So the velocity of B is just going to be 200 times ET kilometers per hour, and there is nothing in the normal direction because velocity is tangent to the path. This is just speed times magnitude. Acceleration. All right, so now we're going to write that it's going to be negative 6 ET plus, and now we get a calculated thing, right? So let's say that, let's do it over to the side. EN is equal to VB EN, sorry, not en. Acceleration of b in the n direction. That's the right way to wear it. All right, it's going to be that over this. And I didn't leave myself enough room. Darn. I should have written it over to the left, but it's okay. Let's see. Let's squeeze it in there. That's going to be 200. We got to be careful here. The acceleration should probably be in terms. Are we going to do? What's it? Wait, these are meters per second. These are kilometers. Yeah, so we got to turn that. You got to turn kilometers per hour into. Yeah. We want to turn kilometers per hour into meters per second squared so that it'll be compatible with these things that we know. And that's where I messed up right down there. Sorry about that. Yeah, that's meters per second squared. Yeah, so we'll take 200 kilometers per hour. We times 1,000 and divide by 3,600 will give us 55.56 meters per second. So this is 55.56 squared divided by 300, which ends up equaling 10.29 meters per second squared, right? So this is going to be 10.29 En. I think I could leave the velocity, just go ahead and leave the velocity as in kilometers per hour, because that's really going to be the most meaningful thing to us. And I think as a general rule, if they give you this for velocity and you're asked for a velocity, give the answer in terms of what they gave you. And if you're given this as an acceleration, give them the answer in terms of that, right? So we're all set, I think, right? So this is meters per second, that's meters per second, yeah. Right, so we've written out what the velocities are for each of the points. Now let's do our coordinate transformation. So we have this and this. Here's J, and here's I. Here. And this angle, okay, so sometimes I like to extend these out. Actually, not sometimes, almost always. I like to extend these out a little bit. And that'll help me figure out where the angle is. That angle is right there. That's our 50 degrees. That theta, right? And so that means that is also theta. Okay, so our coordinate transformation, we want to try to go, let's go to I and J. Is that how I did it? Yeah, I decided to turn this into I and J and to turn that into I and J. So I have been doing this so far always on the top, so we can, and I mentioned to you that we, I'll do it here, but we could do our coordinate transformation where this was I and this was J and this was the other two. And it's best to just keep them in this order right there for right now. All right, so I, if we change I, that looks like a J, man. No, I guess that's good enough. Yeah, that's an I. If we turn I into, or we could do the other way around. Let's take the ET and turn it into I and J. So this is the angle right there too. We know that one has to be true. So this makes this negative cosine of theta, right? And then this one is going to be negative sine of theta, right? If you're not clear with this, go back to the other videos where we break this down and look at it a little more slowly. But you want to get used to making these coordinate transformation arrays. And then in the normal direction, that's going to be a positive sign. And it's going to be a negative cosine of theta. So for the velocity, let's do the velocity transformation first. And we're going to take, all we have for B is this in the tangential direction. So it's in the tangential direction and we want it in the I and the J, we go by rows, right? But previously when we did the transformation, we went by columns. But here we have ET and we want I and J, so we're going that way right there. So we got the velocity of B is going to be equal to 200 times the cosine, let's say that's going to be negative right there, right? Because it's negative. I'll put it in there. But it's that 200 times that I times the cosine of, and there was 50 degrees is what we were given by here, is theta. I, and then plus, but this is negative, so a negative 200 sine of 50 J. And if we do the math in that, it comes out to negative, for some reason I did meters per second. Okay, so I'm going to have to recalculate this. I don't know why I gave my answer in meters per second. Yeah, made more. I told you just a second. You should give it to what it's in. But let me. I'll do the math out live here. So 50 cosine times my 200 comes out to negative 128.6 I plus 200 times the sine of 50, so we get negative 153.2 J. And these are kilometers per hour. All right. Now we could go to the thing we wanted to do all along in part A, is find the difference between them. So we're going to subtract A from B. So here is A right there. So the velocity of B with respect to A is going to be equal to, well, first in the x direction, we do B first, right? And go negative 128.6 minus A, 240. I. And then here we go, right here, it's, for B, it's just this because there is no y component in the A right there, right? J. So what we find VB with respect to A is simply going to be, 240. So it's going to be negative 368.6 I plus negative 153.2 J kilometers per hour. Right? And we might want the, they didn't tell us for sure, but a lot of times that's all well and good, but I would rather have what the magnitude and angle of them are going to be, right? So take the square root of that negative 368.6 squared and the negative 153.2 squared. Normally I just don't bother writing those negatives because they're getting squared anyway, so it doesn't matter. So I square that, and then I square that, and I add them together, and then I take the square root, and we get 399.1 kilometers per hour, and the angle of the B with respect to A. I should say maybe put a velocity thing in there, a little subscript in there, but I didn't. But 153.2 and 368.6, and I'm ignoring the negative signs in there because that just tells me it's in the lower left-hand quadrant when I'm done. But as long as I have the y over this, we know it's going to be with respect to horizontal, right? So we just take the 153.2 and the 368.6, divide them, and take the inverse tangent, and we have that it's 22.57 degrees, right? So when we go to give the answer, we'll say that it's 399, leave off the, just do 3 sig figs, good enough, kilometers per hour, and at this angle, that's coming down in that quadrant right there, right? And now for the acceleration, it's a little bit more involved because we have to turn this acceleration into I and J, so there's a couple more terms in there, right, as we're coming through here. So we take the acceleration of B, and I don't, in the previous example of a coordinate transformation, I probably skipped, I probably like went by, I think I did, yeah, I probably like broke the thing out and then wrote it out and then wrote it out again. But here I can just go ahead and take a look at the I's right here. So I go -6 right here times this plus 10.29 times that is going to be the I, right? So let me write that out. I go -6 times the negative cosine of 50. I ended up putting it up there because I forgot. I knew that one had to be negative, but it's going to be plus, right? And now we're going to have this times that right there, right? To get that. So it's going to be the 10.29 times the sine of 50. I plus -6 times the sine of this, right? As we're going, yeah. Is that correct? Let me double check. No. -6 times the negative, this one right here, because we want to get the I, we want to get the J, right? So we're going to turn this ET into J here. So we take a -6 and then times that negative sine of 50. I hope I did that right. Plus, then we take this guy right here, and he's going to be, he's the EN, and we want to turn him into J. So it's going to be the 10.29 times the negative cosine of 50 J. So let me see. Hopefully I did that right. I'm going to double check everything. Yes. And if I do all of that, I end up getting acceleration of B is equal to 11.74 I plus -2.018 J. And these are meters per second squared. But I want to get, I was asked for the acceleration of B relative to A, this guy right there. So I say the acceleration of B with respect to A is going to be, let's see, in the I direction, B with respect to A. So we're going to take B and we're going to subtract out A. So that's going to be 11.74 minus, and that's 10. Is that right? Minus 10? Did I do that correctly? Minus, I said minus 10. Where did I get minus 10 from? 1 second here. A is increasing at 10, so I must have messed something up in my original here. I said that he was negative, and he should have been positive. Interesting. Okay. I messed things up a lot. So there's me somewhere else, probably last year. I don't know. Be neater than this. That's what I wrote down on the top of my page. But I have a minus. So it's not minus. So it should be 10, minus 10. And was this minus? I don't think it was. I think this was positive, right? Because we had a minus, and that was positive. So that makes sense that it came out to that amount. Okay, so it's going to be small. And that's I. And then we're going to go, this one is just B, and so it just ends up being, yeah, meters per second squared. I think that's right. I think my thing previously was incorrect. All right, so what we end up having here, I should probably have written it out right there. We could 1.74 I plus negative 2.018 J meters per second squared. And we want to get the magnitude. So that's 1.74 squared. I wish I had more sig figs than that. But, you know, you subtracted the thing out, so you only had, that's all right. And because my thing is wrong here, 1.74 squared, 2.018 squared plus square root, I get 2.665 meters per second squared, and then the angle of B with respect to A, but I don't mean that one, you know, I just mean this, yeah. We take 2.018 divided by 1.74, and 2.018, 1.74 divide inverse tangent, we get 49.23 degrees. So if we want to give the answer now, all right, and so that one's negative, but that one's positive, so it's going to be up. It's going to be down and to the right, right? Down and to the right, because it's going downwards, negative, right here, but it's going to the right there. Okay, so the answers are A is going to be VB with respect to A is equal to 399 kilometers per hour at 22.6 degrees in that quadrant, whereas B is going to be acceleration of B with respect to A is going to be 2.67 meters per second squared at 49.2 degrees, and that way. And I hope I didn't make any big mistakes, because I think I'm assuming I made a mistake in my previous in this one, so I might throw this one away and add this one to my notes instead. So there you go, and we'll do another example here, so we really have a lot of things to reference.